Hello again. This is Math 2115 coming to you from the College of DuPage, and the title of this lecture is Fermat's Little Theorem and such. As always, please be an active learner as you watch these videos. The Chinese remainder theorem can help us do computer arithmetic with large numbers. The computer is finite, and so we're interested in ever expanding its reach doing calculations. So suppose that M1, M2, all the way up to Mn are pairwise relatively prime moduli, and let M be their product. The Chinese remainder theorem tells us that A, between 0 and M, this way, can be uniquely represented by this n tuple. Let's look at an example to make this clearer. What are the pairs used to represent the non-negative integers less than 12 when they are represented by the ordered pair where the first component is the remainder of the integer upon division by 3 and the second component is the remainder of the integer upon division by 4? Well, we have the following representations obtained by finding a remainder of each integer when it's divided by 3 and divided by 4. So you see these are the possibilities, because you could have remainders of 0, 0 for the subsequent problems, 1, 1, 2, 2, 0, 3, 1, 0, 2, 1, 0, 2, 1, 3, 2, 0, 0, 1, 1, 2, and 2, 3. So to perform arithmetic with large numbers, we can select these moduli carefully, and each of them is an integer greater than 2, and they're pairwise relatively prime. And then we can do the arithmetic using those n tuples instead. So once we've selected our moduli, we carry out arithmetic operations with large numbers by performing component-wise operations on the n tuples, representing these integers using remainders upon division by m sub I. Once we have computed the values of each component, we recover its value by solving a system of n congruence modulo mi. This method of performing arithmetic with large numbers has several advantages, valuable features. First, it can be used to perform arithmetic with integers larger than ordinarily can be carried out on a computer. Secondly, computations with respect to the different moduli can be done in parallel, speeding up the arithmetic. So let's look at an example. Suppose we're performing arithmetic with integers just less than 100 on a certain processor is much quicker than doing arithmetic with large integers. So we can restrict almost all our computations to integers less than 100 if we represent integers using the remainders modulo pairwise, prime numbers less than 100. And these are moduli that are pairwise relatively prime: 99, 98, 97, and 95. No common factor greater than 1. So by the Chinese remainder theorem, every non-negative integer less than their product, which is 89 million plus, can be represented uniquely by its remainders when divided by these four numbers. So for example, we can represent 123 as, and here we're taking the remainders upon division by these in that sequence, 33, 8, 9, and 89, because it's the solution to those. Similarly, we represent 413,456 as 32, 92, 42, 16. So to find the sum, you add them component-wise and get this, and then you can do reduce these, and we find that the sum of those two is 65, 2, 51, and 10. See, I added them component-wise and reduced the numbers to their appropriate modulus. So to find the sum, that is, it's 65, 2, 51, and 10, we can solve this using the Chinese remainder theorem, and this is 537140. Note that it is only when we have to recover the integers 65, 2, 51, and 10 that we have to do arithmetic with any integers greater than 100. Now, particularly good choices for moduli for arithmetic with large numbers is the set of integers of the form, and these are the Mersenne numbers, 2k minus 1, where k is a positive integer, because it's easy to do binary arithmetic modulo such integers, and because it's easy to find sets of such integers that are pairwise relatively prime. And in fact, this second reason is a consequence of the fact that the GCD of those two big numbers is 2 to the GCD of AB minus 1. I have asked this question proving this as a problem on some tests, so that would be a good exercise for you to think about. Suppose, for instance, that we can do arithmetic with integers less than 2 to the 35. Now, that's a really big number, easily on our computer, but that working with larger integers requires special processes. We can use pairwise relatively prime modulus less than 2 to the 35 to form arithmetic with integers as large as their product. So, for example, we could take 2 to the 35 minus 1, 2 to the 34 minus 1, and so on down to 2 to the 23. Those are pairwise relatively prime. Because the product of these 6 moduli equals 2 to the 184, we can actually perform arithmetic with integers as large as 2184. By doing arithmetic modulo each of those 6 moduli, none of which exceeds the storage limits of our computer. Kind of a big deal. You can see there are several orders of magnitude difference between this number and this number. Now we move on to a very important theorem called Fermat's little theorem. And there is a Fermat's theorem. It was called Fermat's last theorem. This is very famous and very interesting history and discussion, but it's beyond the scope of this course and really is not used in computer applications. So we'll stick with the little theorem. So this device, or in fact, let's just state it. Fermat's little theorem. Oh, like so many other things, Fermat didn't actually prove this, or at least publish a proof for this, but Euler cleaned up much of the things that Fermat left incomplete, and that actually happened with this one as well. Okay, so here's the statement of Fermat's little theorem. If p is prime and a is an integer not divisible by p, then a to the p minus 1 is congruent to 1 mod p. Furthermore, for every integer a, then that's the same thing as saying a to the p is congruent to a mod p. So this is Fermat's little theorem, and it turns out it has big applications. And one of the applications is we're going to use this to compute the remainders modulo p of large powers of integers. But first, let's look at a charming proof of this. This is a charming and visual proof, and so we'll do this one instead of the one that Euler provided. Okay, so to set up the visual then, assume that a is a positive integer and consider the possible strings of p necklaces, p symbols. And we're using an alphabet with a different things. And let's suppose, for sake of just an example, if p is 5, so each string is going to be 5 long, and a is 2, that means my alphabet is 2, and let's just assume it's a and b. Then there are 2 to the 5th equal 32 strings of length 5 possible, and here they all are. But now what I'm going to do is I'm going to break these into 2 groups. Some of these strings will be pure, all 5 A's and 5 B's, and I'm going to put them down here. But the others are going to be friends if I make them into necklaces, and that is, these are all the strings that have 4 A's and 1 B. This is 3 A's and 2 B's. This is 3 A's and 2 B's arranged like that, and so on and so forth. So I list all of these possibilities. These are the pure ones. These are the ones that aren't pure. Now, it's very clear that 32 minus 2, the total of 32 minus these 2, is divisible by 5. Now, that's what we're going to show in general. So what we're going to do then is we're going to take a set S, and S is made up of several copies of another string called T, and T cannot be broken down any further into repeating strings. So this is the S and T playing the role of A and P. Okay, so that means that if S is built up of several copies of T, and T cannot be broken into further strings, then the number of friends of S, these are friends, or the ones that are in a row, including S itself, is equal to the length of T. So each of these was 5 in our case, so that's what we have. So for example, if we start with a string, and this is, we're using different numbers here, but we start with this string, what's really being repeated is ABB. And so if we think about the following 3 strings this is ABB, ABB, and ABA. There aren't any others, because that's exactly 3 symbols long. It can't be further broken down. So to complete the proof, what we see is that some strings contain P identical symbols. There are exactly A of those, and the rest of the strings use at least 2 distinct symbols. And so the second category of set contains AP minus A strings, and they may be arranged into groups of P strings, one group for each necklace. Therefore, AP minus A must be divisible by P, as promised. And that is equivalent to Fermat's little theorem. The proof, and you want to think about this proof, I suppose. The proof that Euler gives is cuter than that, and involves this identity: x plus y to the p is congruent mod p to x to the p plus y to the p for p of prime. And this is called the Fleischmann's dream, because this is not true with numbers, but sometimes Fleischmanns do. I think that is true. And I have asked people to prove that on exams before as well. But now let's move to an application of Fermat's theorem, which I've also asked on exams. So we want to find 7 to the 222 mod 11. Now you might think, wow, that's a horrible calculation. Not so bad, because we're going to use Fermat's little theorem to calculate that mod 11, instead of using the fast modular exponentiation algorithm that we covered earlier. Okay, so we know that 7 to the 10 is congruent to 1 mod 11. That is Fermat's little theorem applied to modular 11. So that means if we raise both sides to the k power, that this is going to be congruent to 1 for every positive integer k. So we will use properties of exponents. So 7 to the 222 is equal to 7 to the 22 times 10 plus 2. What I'm doing here is I'm dividing 222 by 10. It goes 22 times and 2 left over. And I can rewrite this way, but I know that this number is 1 to the 22. And 1 to the 22 is just 1 times 49. And changing 49 to mod 11, we get that it's congruent to 5. Therefore, 7 to the 222 mod 11 is equal to 5. So this illustrates how we can use Fermat's little number to compute a to the n mod p, and use this to calculate larger ones. Here's the general statement of the properties of exponents. So hence, to find a to the n mod p, we only need to compute a to the r mod p. And this will take advantage of this simplification many times in our studies of number theory and encryption. Previously, we showed that an integer n is prime if it's not divisible by any prime, and p is less than or equal to the square root of n. Unfortunately, this criterion shows that a number is prime is an inefficient way to go. It doesn't work for really big numbers. And so you really can't be doing many trial divisions. So we're going to consider something called pseudo-primes, which leads to some tests that are used for prime numbers. And this is a big deal in number theory, and it's also a big deal in computer security. Now, a little bit of historical background. You see, some Chinese mathematicians long ago believed that, and again, they're being given credit for these discoveries, that n was an odd prime if and only if 2 to the n minus 1 is congruent to 1. Now, if this were true, we'd have an efficient primality test, but they believed that this was true not only when it was prime, but they believe that was true for any number. And it certainly is true for an odd prime because p is prime and 2 to the 5 minus 1 is congruent to 1 mod 5. So we know this is correct. But it's unfortunately, there are composite numbers such that 2 to the n minus 1 congruent to 1, and they are not prime. And such integers are called pseudoprimes to the base 2. Let's do an example here. This is a little bit of an existence proof. The integer 341 is a pseudoprime to 2 because it is a composite number. It is 11 times 31. And as you can show, is that 2 to the 340 is congruent to 1 mod 341. You should, in fact, practice that and see what happens with that. So we can use an integer other than 2 as the base when we study pseudoprimes, and if we let b be a positive number, if n is a composite positive integer, then b to the n minus 1 congruent to 1 mod n, then we call that a pseudoprime. And so this is a generalization of prime numbers. So given a positive integer n, you can determine whether this is congruent to 1. It's a useful test, and it provides some evidence, not conclusive evidence, that n is a prime. Now, if we perform similar tests using bases other than 2, we obtain more evidence as to whether it's prime. If it passes all these tests, then we say, well, there's a good chance it is prime. It still can. But, and just to give you an example of the numbers, if we're talking about all the positive integers that are less than 10 to the 10, which is an enormous number, there are many primes, but only these many pseudoprimes. Okay, so you see this approach cannot really distinguish between primes and pseudoprimes just by choosing many bases. So this is something that people have generalized and studied. And a composite number n, integer n, which specifies the congruence b to the n minus 1, congruent to b mod n for all positive integers b, where the greatest common divisor of b and n is equal to 1, is called a Carmichael number. And that's someone's name, that's why it's capitalized. These numbers are named after, I guess I already said that. Now, there are Carmichael numbers. 561 is a Carmichael number. To see this, first note that it's composite because it's 3 times 11 times 17. And also you can see that it's if b is relatively prime of 561, then it's also then also you have GCD of this, this, and this are also equal 1. So if we use Fermat's little theorem, we can find out what b squared is. B to the 10th and b to the 16th are all congruent to 1 with these mods. And that means it follows that 560 is congruent to 1. Mod 3, b to the 560 is congruent to 1 mod 11, and b to the 560 is congruent to 1 mod 17. So this is a Carmichael number because it satisfies the definition. Now, one can prove, and number theorists do, that there are infinitely many Carmichael numbers, but more delicate tests described can be used to test for primality. And this is what's being done a lot with the great internet Mersenne prime search. And so, again, that's an important activity for the mathematical community, and I talked about that in an earlier lecture. This leads us to consideration of primitive roots and discrete logarithms. In the set of positive integers, if b is greater than 1, then and is equal to b to the y, we say that y is the logarithm of x base b. Well, we can actually define the concept of logarithm modulo p of positive integers where p is a prime. And what we need a definition. So the definition is a primitive root modulo a p prime p number. So this is a primitive root modulo p is an integer r in which every non-zero element of zp is a power of r. That is r sort of, if you start raising it to powers, you will generate zp. Let's determine whether these are primitive roots of mod 11. Well, that means we have to get everything in mod 11, that is 0 through 10. We need to be able to establish that by raising 2 and 3 to various powers. Well, here we raise 2 powers, we get 2, 4, and so on and so forth. So every element of z to 11 is a power of 2. So that's a primitive root. Similarly, if we do 3, we will get, actually we were doing a test, so 2 is a primitive root. Here we compute all the powers, and because not all the elements of z to the 11 are powers of 3, this is not a primitive root. An important fact in number theory is if there is a primitive root for every modular zp, if p is prime, there is a primitive root modulo p, okay, and that can be proven. And so there's a primitive root, and that leads us to this definition now of logarithms. So suppose that p is a prime and r is a primitive root modulo p, and a is an integer between 1 and p minus 1 inclusive. If r, that's the primitive root, raised to the e mod p is equal to a, and e is between 0 and p minus 1 inclusive, e is the discrete logarithm of a modulo p to the base r. And we can write log r of a is equal to p where the prime p is understood. And so we can actually do some of this. Find the discrete logarithms of 3 and 5 modulo 11 to the base 2. Well, we know that 2 modulo 11, we computed all those. So, so the discrete logarithms of 3 and 5 are 8 and 4 respectively. Now, the discrete logarithm is a valuable tool in determining prime things, and you can see in the marginal note, the discrete logarithm problem is hard because is actually pretty difficult, and in fact there's no polynomial time algorithm for solving it, and that makes people more comfortable with the encryption algorithms that we will be discussing soon, because they're hard to break, because you have to solve this problem in order to encrypt the data. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. And very soon we'll be discussing important computer applications of what we have just learned. May God bless you all.